Heat capacity, temperature and heat. If you take a can of cola from the refrigerator and leave it on the kitchen table, its temperature will rise rapidly at first, but then more slowly until the temperature of the cola equals that of the room. The two are then in thermal equilibrium. In the same way, the temperature of a cup of hot coffee left sitting on the table will fall until it also reached room temperature. In generalizing this situation, we describe the cola or the coffee as a system with temperature T system S, and the relevant parts of the kitchen as the environment with temperature TE environment of that system. Our observation is that if Ts is not equal to Te, then Ts will change. Te may also change some until the two temperatures are equal, and thus thermal equilibrium is reached. Such a change in temperature is due to the transfer of a form of energy between the system and its environment. This energy is thermal energy or internal energy, which is collective kinetic and potential energies associated with the random motions of atoms, molecules, and other microscopic bodies within the object. The transferred internal energy is called heat and is symbolized Q. Look at this. If the T environment is larger than T system, heat is positive when internal energy is transferred to a system from its environment. We say that the heat is absorbed. If the TE equal to TS, nothing happens. If the TE is smaller than TS, heat is negative when internal energy is transferred from the system to its environment. We say that heat is released and lost. Definition: heat is the energy that is transferred between a system and its environment because of a temperature difference that exists between them. Recall that energy can also be transferred between the system and its environment by means of work, W, which we always associate with a force acting on a system during the displacement of the system. Heat and work, unlike temperature, pressure, and volume, are not intrinsic properties of a system. They have meaning only as they describe the transfer of energy into or out of a system. Measuring heat unit. The calorie, CAL, was defined as the amount of the heat that would raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 Celsius. In 1948, the scientific community decided that since heat, like work, is a transfer energy, so the metric system unit for the heat should be the same as that energy, namely the joule. The calorie is now defined to be 4.1860 joule exactly, with no reference to the heating of water. 1 calorie equals 4.186 joule exactly, and 1 capital K is thousands calorie. In the British system, the corresponding unit of heat was the British thermal unit, defined as the amount of heat that would raise the temperature of 1 pound of water from 63 degrees of Fahrenheit to 64 degrees of Fahrenheit.
We've all felt how much warmer our hands become when we rub them together rapidly. Any two objects rubbed together will generate heat. Here is one such pair of objects, a wooden board and dowel. If we rub them together this way, not much happens. Let's try a little more speed and pressure. Now we clearly see the effects of heat generated by the friction between moving objects.
We'll use this plastic tube loaded with lead shot to show how mechanical energy is transformed into thermal energy. The temperature of the lead shot is initially 21 degrees Celsius. We'll perform mechanical work on the lead shot by flipping the tube end over end. Each flip raises the shot 1 meter, then drops it back to the bottom of the tube. We will flip the tube 10 times for a total lift and fall distance of 10 meters. The lead shot is now at 21.5 degrees Celsius. The mechanical energy of lifting the shot has been transformed into thermal energy, raising the temperature of the lead shot. We'll use this cork popper to demonstrate conversion of mechanical energy to heat and then back to mechanical energy. This hollow cylinder spins between two wooden arms, which can be squeezed down onto the metal. A small amount of water is put inside the cylinder. Then a cork is tightly pressed into the top. The motor is switched on and the arms are squeezed down on the rotating cylinder. Friction between the cylinder and the arms heats the water and turns it into high-pressure steam. The thermal energy in the steam pops the cork into the air.
The absorption of heat by solid and liquids. Heat capacity C. The heat capacity C of an object is the proportionality constant between an amount of heat Q that the object absorbs or loses and the resulting temperature change delta T of the object. That is Q delta T proportionality. Okay, delta T is T final minus T initial.
When we put a flame to this balloon filled with air, the balloon explodes. But an identical balloon filled with water easily withstands the flame. The high heat capacity of the water allows the balloon to absorb large amounts of heat without a large rise in temperature.
When we touch this paper cup with the flame from a torch, it quickly catches fire. When we fill an identical cup with water and bring the flame up again, the cup withstands the flame without harm. The flame can play onto the cup long enough to boil the water inside without burning up the cup.
Specific heat C equal to capital C over M. Two objects made of the same material, say marble, will have heat capacity proportional to their masses. It is therefore convenient to define a heat capacity per unit mass or specific heat C. That refer not only an object but to a unit mass of the material of which the object is made. Molar specific heat. In many instances, the most convenient unit for specifying the amount of a substances is the mole, where 1 mole equals 6.02 times 10 to the 23 power elementary units of any substance. Okay. When quantities are expressed in moles, the specific heat must also involve moles, rather than a mass unit. It is then called a molar specific heat. Okay. The following table shows the values for some elementary solids. Each consists of a single element at room temperature. Okay, look at this one. This is specific heat. This is molar specific heat. We see all these lead, tungsten, silver, copper, aluminum. They have quite different number of the specific heat, but their molar specific almost the same, around 25. We will explain it later.
Different metals have different specific heats. We'll demonstrate that using equal masses of lead, aluminum, and steel shot. 75 grams of each metal are placed inside soda cans that are sealed and put into boiling water. When the metal samples reach 100 degrees Celsius, we'll pour each of them into 50 grams of water and measure the increase in temperature of the water. The lead sample increases the water temperature 4 degrees Celsius. The aluminum sample increases the water temperature 14 degrees Celsius. The steel sample increases the water temperature 8 degrees Celsius. Aluminum has the highest heat capacity of the 3 metals and lead the lowest.
We'll use these 3 metal cylinders to demonstrate how heat capacity varies for different materials. The cylinders, made of aluminum, steel, and lead, have equal mass. They are slotted to slide on small rails in this frame, which is covered with a thin sheet of beeswax. The rods are heated in boiling water to 100 degrees Celsius. When placed on the rails above the wax, they begin to melt their way down through the sheet. Aluminum, with the highest heat capacity of the 3, travels farthest, followed by steel, then lead.
An important point in determining and then using the specific heat of any substance, we need to know the condition under which heat transfer occurs. For solid and liquid, it turns out that specific heat under constant pressure and constant volume for any solid or liquid differ usually by no more than a few percent. Gases, as you will see, have quite different values for their specific heat under constant pressure condition and under constant volume condition. Heats of transformation. Matter can exist in three common states. In the solid state, the molecules of the sample are locked into a fairly rigid structure by their mutual attraction. In the liquid state, the molecules have more energy and move about more. They may form brief clusters, but the sample does not have a rigid structure and can flow or settle into a container. In the gas or vacuum state, the molecules have even more energy and free of one another and can fill up the full volume of a container. When energy is absorbed by a solid or liquid, the temperature of the sample does not necessarily rise. Instead, the sample may change from one phase of state, that is solid, liquid, gas, to another phase or state. To melt a solid means to change it from the solid state to the liquid state. The process requires energy because the molecule of the solid must be free from their rigid structure. To freeze a liquid to form a solid is a reverse of melting and requires an energy be removed from the liquid so that the molecules can settle into a rigid structure. To vaporize a liquid means to change it from the liquid state to the vacuum or gas state. This process, like melting, requires energy because the molecules must be free from their clusters. Condensing a gas to form a liquid is the reverse of vaporizing. It requires that energy be removed from the gas so that molecules can cluster it instead of flying away from one another. Heat of transformation. The amount of energy per unit mass that must be transferred when a sample completely undergoes a phase change is called the heat of transformation, L. So, when a sample of mass M completely undergoes a phase change, the total energy transfer is Q equal to Lm. L is the heat of transformation. Mass is the mass. In this case, process T is constant, does not change. Look at that. This melting point, this boiling point, this hydrogen, this water, and so on. So water is pretty sample. Question A. How much heat must be absorbed by ice of mass M 720 gram at minus 10 degrees of Celsius to take it to liquid state at 14 degrees of Celsius? From minus 10 degrees to 15 degrees, the water undergoes three processes. First, from minus 10 to 0, that's the heating, okay? And at 0 degrees Celsius, phase change from solid ice to a liquid state. And then from 0 to 15, the liquid increased the temperature. So let's see that. Q1 is ice. Ice from what? From minus 10 to 0. Okay? Now we put number inside. Okay. The mass is 0.72 kilogram. This is to 0, minus 10. We get number. And the second is the phase energy. Rm. We can check the number. Air phase change from liquid solid to liquid is 333, and multiply. And the last is from 0 to 15 degrees Celsius, a liquid. So this you have your water, a liquid. This is ice. They're different. Okay. The final is 15. This is 0. Okay. So we get 3. So altogether we need 3. Put them together. Okay. About 300 kilojoule. Question B. If we supply the ice with a total energy of only 210 kilojoule as heat, what then are the final state and the temperature of the water? So look at these 3 processes. We have 3 questions. Whether they can reach the 0, in that case the all ice, or whether they can have a phase change completely become a liquid, or just part phase change, part cannot. Or last, they can have a phase change, but the temperature are not enough to 15 or something like that. So we check. Okay. First we see from minus 10 to 0, we need 15.6 K. We have as calculate. Phase change is this one. So we see this one, we can finish this one, but not this one. That means only part of ice become the liquid, and part of ice stay as ice. So let's see, 210 minus 15 point, you have 164 kilo. And total phase change, we need 239.8. So our energy is not enough. Only we have a part. We divide it by the air, we get about 0.56 kilo can become water. Okay, and other is left as ice, a degree of 0 degree of Celsius. So 580 degree become the water, 140 degree ice, all at the temperatures 0 of Celsius. Sample. A copper slug whose mass MC is 75 grams is heated in a laboratory oven to a temperature T 312 degrees of Celsius. The slug is then dropped into a glass beaker containing a mass M water, 220 grams of water. The heat capacity Cp of the beaker is 45 calories per Kelvin. The initial temperature Ti of the water and the beaker is 12 degrees Celsius. Assuming that the slug, the copper, the beaker, and the water are an isolated system, and the water does not evaporate, find the final temperature T final of the system at thermal equilibrium. We see that both the water, beaker, and the slug, the copper, they have energy. Put together is constant before. And during the heating, they have a change. Okay. But every change, this change 0. Okay. What it means, we do this data on both sides. This is change. This is change constant, 0. What is this change? This is the heat. We have only heat involved, no work involved. So this is water, he absorbs heat. Okay. This is the fever, he absorbs heat. This is a copper, they release the heat. So anyway, this put together is 0. And that's what is QW? QW equal to C water, M water, T final of the Ti. What is B phase is C given T final of the T initial. They're the same. And finally, the copper. The copper is C copper, M copper, T Fi. T is larger than this one. So this negative number, it released the heat. The water and the big absorb the heat. So we put these 3 in this equation. We can find TF. Once we find that TF, we put it aside, we get a 3 number. CC 0.6C, MC is 75, we just so about 20 degrees Celsius. And we put the TF inside where the QW equal to this. QB absorbed, and the QC is negative number.